All right, so you watched that video last night, and in that video I talked about all of these IUPAC allowed substituents. In fact, there's many, many more than this, but these are kind of the trimmed down version I want you to know. I want you to know the difference between a propyl group and an isopropyl group, and then I want you to know all of the different butyl groups. They have different amounts of branching in them. So what I have here is you can kind of see a big black chain. That's my parent, right? So the big, long, black horizontal zigzag is my parent. And then off of the far left, I've got a propyl group, just a regular propyl group, 3 carbons. But you see how an isopropyl group, the next one over, also has 3 carbons, but now it's branched. Iso means that it's branched at the very, very end. So it's just got that little branch there. And then as we go over next, we've got this butyl group right here. That butyl group just has 4 carbons. But you see how isobutyl group right here also has 4 carbons, but it's branched at the end, so we tack on that iso to say that it's branched at the very end. All right, sec-butyl is a little bit weird. Instead of being branched at the end, it's actually branched closer to the parent. So we have to account for that by saying this is sec-butyl. And then tert-butyl looks what I call like a duck foot. So it's got the 3 prongs coming off. You may notice in the book that they use the naming convention shown in blue. That's also systematically allowed. Students will say, well, which one's preferred? I'll say, really, you can use either, and I'll understand what you're talking about. However, most chemists will use the naming system shown in red. So if you can, try to be familiar with the red one, because that's what the Klein textbook uses throughout the book. Make sense? All right. So like I said, make sure that you watch the bicyclic naming video tonight for your next pod. All right. Now we get to do conformational analysis. So I've got a warm-up question for you. Let's compare the following molecules. Are these the same molecules or are they different molecules? How would we describe these two? Are they constitutional isomers? Let's name them. Name the one on the left. What's the longest carbon chain? Say 1, 2, 3, 4, 5. Got a methyl group coming off of carbon 3. So what would we name this? 3-methyl pentane. So pent means 5. So this is 3-methyl pentane. Let's do the next one. What's the longest carbon chain in the next one? 1, 2, 3, 4, 5. It's got a methyl group coming off of carbon 3. What's the name of this? 3-methyl pentane. All right, so let's go back to the original question. Are these different compounds or are they the same compound? Same compound. Why are they drawn differently? Because I did that? Yeah. But what were you saying though? The bonds can rotate, right? If we think about sigma bonds can rotate freely in space. So in solution, these things will flop around in space. So we can draw them right side up, upside down, spun around 3 times. It doesn't really matter. It's the same molecule. All right, so let's make a note of that. And I abbreviate compound like this. So same compound, and we'll say sigma bonds can rotate. All right, so this is exactly what conformational analysis is it's the study of bond rotation. All right, so it does get a little bit confusing, but do you remember me talking about that website that I like, the Master Organic Chemistry? And I said he's got a lot of good cat references. I got him. All right, so in the first one, if you look in, you see how the cat on the far left is shown with dashes and wedges? What does the wedge mean? It's closer to you. What does the dash mean? Further away. So they're drawing the cat over here using line wedge notation, where the wedges mean it's coming out of the board, dashes are going into the board. You can also draw these using a sawhorse conformation. We really don't do that in organic chemistry very often. We're going to avoid that. And then the next one we do is kind of this head-on view, down the cat. So kind of see how the head is represented with an H, the tail with a T, and each of the feet going down. All of these are cats. We're just choosing to represent them or draw them differently using different drawing techniques. So what we're going to do most of this section is talk about how to draw Newman projections or Newman structures. All right, so let's consider ethane. All right, so ethane is how many carbons long? 2. Eth is always 2. All right, so let's say we have 2 carbons long. We must have CH3 groups coming off of each side. So I'm going to do CH3 groups using dashes, kind of like they did with that cat picture up above. And I'm going to color code all of my protons. So I've got a black one here, got a red one here, blue one here. I'll do green, orange, and let me change this to purple. All right, so you see how I've color-coded all my protons? All right, now what we're going to do is change this from a bond line notation to a Newman. All right, and I'll show you the trick that I always do is I imagine a little eyeball kind of looking down this bond, right? So imagine you're a person looking down that carbon-carbon bond. All right, if we think about that, we're going to have 2 hydrogens sticking up and 1 sticking down and a carbon in the center, right? All right, my question for you is what's going to go to the top left? Is it going to be red or blue? Red. Imagine we're looking down that bond. Blue. So if I'm looking down that bond, the red proton is coming out towards you. The blue is going into the board. Imagine that I swing around. Which one's going to be to my left? It's a little bit weird, right? So if the blue is going into the board, so imagine it's like this, right? So blue going into the board, red's going out towards you, and I swing it around. The blue is going to be to the top left, right? So we can plug this in there. And then we can say the red one must be to the right, and the black one must be pointed down. So it is a little bit tricky. The main thing to remember is that the dashes are going into the board, so it must be on my left-hand side of that little person looking down. In fact, if you want to draw this as a stick figure, you're more than welcome to. I guess it's not really a stick person. That's just a giant eyeball on a body. But you get the idea. All right, so that's my front carbon. Front carbon is always shown just as a cross like that with 3 branches. All right, back carbon is represented as a circle. The circle means that it must be behind. So the circle always, always, always represents the back carbon. The cross, where you see it connect, is always going to be the front carbon. And in the back, we're going to have 3 different groups. What's going to be sticking straight up in the back? The green proton. All right, now the trickier part. What's going to be on this side now? Is it going to be purple or orange? Orange. Let's think about it, right? If we're looking down through this, let's ignore the front carbon now, focus exclusively on the back carbon. The purple hydrogen is going to be coming out towards you, while the orange one's going into the board. And if we imagine that, which one's going to be on the right? The purple one. So we can go ahead and we can say, well, the purple hydrogen must be here, and the orange one must be there. So this is a Newman projection. Remember, the most important thing that students mess up is that the circle indicates the back carbon. Does this make sense? Yeah. So you can imagine viewing the other direction, right? However, if that were the case, our Newman projection would be represented differently. Would it be a different molecule? No, it'd be looking at the cat from the opposite end, so to speak. Yeah.
What if you have multiple carbons? You just drop it in your
That's a good question. Right now, we're going to stick with just ethane, and then we'll get into more complicated examples where we have more than one carbon. This can only be used to view down a single carbon-carbon bond, if that makes sense. All right, so now what I want to do is take an example where we do a bond rotation. And I'm just going to redraw what we have up there. So front carbon we know is going to be this three-way cross. We said that the blue would be to the left, red would be to the right, black would be underneath. That's our front carbon. Our back carbon has prongs coming off of it. We have green on the top, purple on the bottom right, and orange on the bottom left. All right, so what I imagine doing, so I say, all right, we're going to focus only on the front carbon, and I'm going to pull this hydrogen down here, but if that happens, this hydrogen's also going to pivot up here, and this one's going to pivot right here. How many of you have been through one of those three-prong turnstiles when you go into an amusement park or a subway station? It's kind of like that. So if you've ever gone into a subway and you have to push those three prongs, it's going to click over. All right, so now let's imagine that. This is a 120-degree pivot. The back carbon is going to be completely static in this case. It's not going to be moved. So we're just going to keep the back carbon as is, which means the green proton is going to remain where it was. Same thing with the purple, same thing with the orange. But what's going to be right here now? The blue. All right, so we pulled that blue proton over clockwise. We pulled the red one down here, and that means that the black one must be right there. Students will say, does it matter that we go clockwise? No, you're in charge. You could have rotated it counterclockwise too. However, the sequence of your colors would have changed, right? Same thing with the back carbon. Students will say, well, would it be okay to move the back carbon and not the front carbon? Yeah, that's also acceptable. The idea is we're just rotating that single bond 120 degrees. So we can rotate it either direction using the front carbon or the back carbon if we want. All right. This is a little bit interesting though. So we're going through here, but we're also missing an intermediate step. All right, so let's imagine instead of 120 degrees that we only do 60 degrees. So what I'm going to do is I'm going to erase this right now, and we'll kind of backpedal a little bit, and we'll say, all right, let's imagine we do smaller moves. So we'll move this 60 degrees, we'll move this 60 degrees, we'll move that 60 degrees. All right, so we're doing half a rotation. Does that make sense? A half rotation, not a full 120 degrees. All right, if this happens, we said our back carbon isn't going to be moving, so we can even just fill in our back carbon as is. We can say, all right, if the back carbon's not moving, that green proton's going to be where it always was. Same thing with the purple. Same thing with the orange. All right, where's the front carbon going to be, though? How would we represent that? Yeah, blue H on top of the green H. So here's where we get to be a little artistically creative. Oh, let me fix this. It's kind of hard to show it perfectly overlapping without making a giant mess of things. But can you kind of see how I'm trying my best to represent the purple and green as being overlapped, the red and blue as being overlapped, and then the orange and black as being overlapped? And then we can say, all right, what if we take this move it 60 degrees more. So another 60-degree twist. Where would we be? Yeah, we'd go back to this one. So really, we can either do a full 120-degree twist, or we can do a 60-degree twist followed by another 60-degree twist. Does that make sense? They look pretty different though, and that's what I wanted to talk about, was the names for each of these. On the bottom, this is referred to as an eclipsed conformation. Does anybody know why they say it's eclipsed? Yeah, because they overlap, just like a solar eclipse would be overlapping moon and sun, for example. So eclipse conformation makes a lot of sense. All right, the top two look different, so we call these staggered. Let me actually shrink this down. All right, now conceptual question for you. Which conformation do you think is most stable, eclipsed or staggered? Staggered. Why staggered? Yeah, because the hydrogens in the staggered conformation actually can get out of the way of one another a bit more. In the eclipse conformation, they're going to be feeling each other through space a little bit more. So if we were to actually measure the distance between the green and the blue hydrogen down here, they'd be a lot closer than they would be right there, right? So that would make them a lot less stable. All right, so now let's imagine this. We often like to show this using energy diagrams. So I'll just write energy here, and then rotation down here. All right, so we said staggered is more stable, so it's going to be lower in energy than eclipsed. So maybe we go up in energy to our eclipse conformation, and then we go back down to staggered conformation. Does that make sense? So we're going into a higher potential energy surface when we are forcing ourselves to go through that eclipse conformation, but it'll quickly fall back down into that staggered conformation because it's more stable. Again, getting back to that idea of the three-pronged turnstile when you go into a subway, right? If you lift that up to its like highest energetic point, that would be the eclipsed energy, and then it would quickly release back down into its neutral position, which would be staggered. Does that make more sense? All right, one thing I will say is when I took this course, I was three-dimensionally challenged. I had a heck of a time figuring out what was going on. How many of you have model kits? If you are stuck, what I do is up here, that bond line structure, I make with a model kit. And then I use those colored balls to represent each different substituent. So maybe a colored ball for each different color hydrogen. And then I physically look down that interior carbon-carbon bond, and I do those rotations with my hand. If you need help with that, please feel free to bring your model kit to my office hours or even to lab, and we can work on that. Students will often ask me, okay, that's great, that's wonderful, but what about exams when it actually matters? I let you use your kits during exams. So try to figure out how to use them now, because it can be a really useful tool if you're three-dimensionally challenged like I was when I took organic chemistry. All right, so let's try a different one. All right, in this one, I want to do butane. All right, what does butane look like? How many carbons are in there? 4. Okay, so I'll do carbon, 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 carbon. And in this case, what I want to do is I want to imagine looking down the interior 2 carbons. So that's looking down the carbon 2 to 3 bond. Does that make sense? But we're not quite done. we have to include everything else that's on here, right? So off this central carbon, we would have 2 protons. One would be a wedge, meaning coming out towards you. One would be a dash going into the board. Same thing over here. Like that. Makes sense so far? All right, and then the question is, well, what do we do with the carbons on the end? Do we need to show dashes and wedges for those? It gets super complicated if you do, so I just say, call these little methyl groups. In fact, some students, instead of writing CH3, will just abbreviate it ME for methyl. So you're welcome to do that too. It's just a placeholder for that CH3 group. All right, so now what we need to do is we need to figure out what the Newman for this would look like. Whoops, don't want that. We're not even going to bother color coding this one. All right, so what I want you to do is to help me with the Newman, and I want you to fill in what goes off all of these pieces. So I'll give you a minute to work on that, and I want you to check with your neighbor to see if you agree. And if you think you got it, give me a thumbs up so I kind of have an idea. You can give me a sideways thumb if you're like, maybe. And then thumbs down if you're like, I'm still completely lost. That's a perfectly valid thumb. There's a few thumbs down. I appreciate honesty. All right. So what I want us to do is to think about the front carbon right here, right? So I'll even highlight it and say, all right, this is our highlighted front carbon. All right, what's sticking up off of those carbons, the arms in the air? Hydrogens, okay? So I'll go ahead and say hydrogen there, hydrogen there. What's sticking down? The methyl, the CH3, right? All right, so we've got that taken care of. All right, in the back, I'll highlight all of this and I'll say, all right, the back carbon, back here, like that. All right, what's sticking up off of the back carbon? The methyl group. And then we've got the 2 hydrogen legs kind of sticking down. So I'll throw them in here and here. All right. So now what we need to do is we need to imagine doing 60-degree twists with this. All right. So we get to decide, do we want to move the front carbon or back carbon? Sure. Let's move the front carbon. So we'll do 60-degree rotation, front carbon. All right, that means our back carbon, you can keep it color-coded if you want. Our back carbon is going to be stationary, which means that CH3 off that back carbon is still going to be sticking up. Our hydrogen is going to be down. And then up here, if we're doing a 60-degree twist, let's just maybe go clockwise for fun. We're going to do a twist like that, right? All right, so if we do that, are we going into eclipsed or staggered if we're doing 60 degrees? Eclipsed, okay? So this front carbon is going to look a lot like this. All right, what group is going to be coming off right there next to the methyl group now? A hydrogen, okay, so I'll go ahead and fill that in. All right, what about down here? A hydrogen. Oop. And our last one, therefore, must be a methyl group, so I'll say CH3. Make sense? All right, let's do another 60-degree twist to get out of the eclipse conformation. All right, so in this one, I'll say, all right, let's continue dragging this hydrogen another 60 degrees. Does that kind of make sense so far? Do 60-degree twist. Again, only moving the front carbon. I won't keep on writing front carbon though. Back carbon, we said, is going to stay put the entire way through. What conformation will we get out now after our second twist? Staggered. All right. what is going to be right here? Hydrogen, okay. How about on the very bottom? All right, and then last but not least, that means we must have a methyl group right there. All right, super exciting stuff, huh? Let's do it again. All right, so this time, same idea. We're only going to be moving the front carbon 60 degrees. And then it'll get more interesting at the end, I promise. So the back carbon is going to stay put. We still have the methyl group sticking up on the back carbon. Nothing's changing with that back carbon. However, we're going to run into another eclipse conformation. All right, so my question for you is what's going to be up here, or in the highlighted spot? The methyl group. That means that the hydrogens must be in the other spots. All right, we're almost there. Bear with me. Do another 60-degree twist. So just like before, we'll twist this front carbon 60 degrees. 60 degrees, 60 degrees. Back carbon during this entire rotating process hasn't changed one bit. Now we'll get a new staggered conformation. What's going to be in the top right-hand corner? The methyl. Okay, so we can fill that in. Means we've got hydrogens down here and down here. One more, and then we'll get to the fun stuff. And this is the last time I'll ask you to do this many of these. All right, so front carbon, 60-degree twist, 60-degree twist, 60-degree twist. You know that the back carbon's going to stay put. We've drawn it the same in all 6 structures, but now we're going to another eclipse conformation. All right, what's going to be next to the methyl group in the back now? A hydrogen. All right, how about over here? In the bottom right, the methyl. And that means we must have a hydrogen right there. All right, if we were to do another 60-degree twist, another 60-degree twist, another 60-degree twist, what happens? We go back to the beginning. So in fact, this is just a rotating carousel. So we can imagine spinning that bond, completes 360 degrees, and we go back to the original conformation, right? So this is just giving us a preview of what happens in 60-degree increments as we do the complete 360 bond rotation. All right, now the interesting part. I want you to rank these in terms of most stable to least stable, and then talk with your neighbor and see if you can agree on why. And I will give you a hint. There may be some ties that occur. So let's talk with your neighbor and see which of these is most stable. And in fact, what I'll do is I'll label these as A, B, C, D, E, and F. Don't worry, I'll fix it. All right, let me flip this question on its head. Which one's least stable? I hear some people saying D. Why? Because the methyl groups are being forced to eclipse one another. All right, so I agree that this would be least stable. This actually has its own unique name. This is eclipsed, and it's called syn periplanar. I don't necessarily care that much about the naming of each of these conformations. I care more about eclipsed and staggered, but syn periplanar just means that they're now in the same plane, and syn means that they're on the same side, right? So the methyl groups are now in the same plane and on the same side. All right, so that makes sense. All right, my question for you next is between, let's just say these two, which one is less stable and why? You think F is less stable? Why?
They're not spread out evenly.
They're not spread out evenly. So like we said, eclipse conformations are energetically pretty unstable. All right, so I'd say, yeah, those are pretty unstable, which means that this one is better. Are there any better structures than E, though? A. Okay, so now if we look at A, why is A more stable than E? Okay, so the methyl groups in A are on opposite sides. We know in space that that's going to be more favorable. They want to spread out and not get close to one another. All right, so immediately we can say A is most stable. All right, and that's because the methyl groups are kind of pointed out and away from one another. All right, so there's a new term we've got to present with E. You see how in E, these methyl groups are kind of bumping up to each other in space like that? This has a weird name. Some people might already know it. It's called gauche. A gauche interaction basically means that there's an electron cloud around both of those methyl groups, and in space, those electron clouds don't like being near one another. So it's kind of destabilizing if it's in this configuration, at least compared to A, where they're on opposite sides. Does that make sense? All right, so let's focus on E for a second. Are there any other conformations that are about the same as E? Why C? Because it also has a gauche just on the other side. All right, so if we look at this one, let's label this as gauche. All right, which one's more stable, C or E? They're the same in terms of their energetic stability. In fact, they're mirror images of one another, so they must be the same. All right, so we've got most stable as A. C and E, I would say, are tied for second. All right, that leaves us with B and F. Are they the same? I'd say they're pretty similar. You see how in B there's a methyl group on top, kind of eclipsed with a hydrogen in the back? Same thing with one of the corners. Looks like the same is true with F over there. So I'd say this would be a tie for third. And we've got third as a tie. Does that make sense? All right, so pop quiz. Which of these are eclipsed? F, B, and D. All right, which ones are staggered? A, C, and E. I will tell you flat out, as an instructor, I have to grade your work. It is a nightmare for me when I have to see you draw eclipse conformations because I can't tell what the heck you guys are drawing. So on exams, what we'll do is we'll focus on the staggered conformations exclusively, just simply because they're a lot easier to draw than eclipse. But I did want to show this so we have a complete picture where we do see the eclipse conformations as well. All right, so now what we need to do is make a little energy diagram, kind of like we did with ethane. All right, we said that A was the most stable, and after 360 degrees, we went back to A, right? So I'll put that low in energy right here. Which one was least stable again? D. Right? You see how that's kind of in the middle? So as we're going from A to D, back to A again, D would be in the middle. So what I'm going to do is put D way up here and say that's the highest possible energy conformation. However, we don't go directly from A to D, we go A to B. All right, but let's look at this first. We said that B is actually higher energy than C. So I'll go ahead and say, all right, B is going to be higher energy than C. Does that make sense so far? And then we said going from C to D, we already knew D was the most unstable. All right, now we need to go from D to A. So we'll go all the way to E. E we said was same energy as C. And then we said F is going to be the same energy as B. So now when we go ahead and we draw this out, kind of have this energetic potential curve. It looks more or less like this as we do the 360 degree rotation going from A all the way to A. All right, so if we look at this, we can actually measure this energetic barrier. This is 3.6 kcals per mole. The energetic barrier between A and the highest energy conformation and D is about 6.0 kcals per mole. All right? And I know a lot of you are thinking, oh yeah, that makes perfect sense. I always measure things in kcals per mole. So what I'll do is I'll give you a general guide. Room temp allows molecules to rotate. If barrier is below 20 kcals per mole. All right, so if we look at this, will this rotate freely at room temperature? Yeah, we've got enough energy to overcome these energetic barriers between A and D, right? Because we know between A and D, that's only a 6 kcal per mole jump that we have to overcome. All right, then the question is, what would happen if we cooled this molecule down to absolute zero, meaning 0 degrees Kelvin? The rotation would stop, and which conformer would be preferred? A. So we can actually do temperature studies on these. The hotter we get it, what do you think happens? It spins faster and faster and faster. When we cool it down, it spins slower and slower and slower, and sometimes it can't even spin at all. So it's an interesting theoretical study that chemists work on. All right. Yeah. 20. Yeah. The other thing that frustrates students a lot is in physics, they tend to use kilojoules per mole. Organic chemists, for whatever reason, a lot of us still prefer kcals per mole. They're still units of energy, though. We just, for whatever reason, have stuck with the old school kilocalories.
Oh, these kilocalories are specifically for that molecule.
This is only for butane right now. As far as we're concerned, though, any single bonds will have enough energy to rotate freely. It's very rare that you'll have a single bond that can't rotate freely at room temperature. Good question. All right, I'll leave you with a problem to chew on tonight. and then we'll check in tomorrow. So draw all 3 Newman projections. That are staggered. And then we'll come back and we'll look at this tomorrow. All right, in this one, we're going to be looking at a specific bond, but let me fill in these remaining pieces. We're going to be looking down this bond. If I wanted to write this out, what could I call this group? Ethyl. We can abbreviate ethyls as ET. We can abbreviate methyls as ME. And then what about this group? Another ethyl group. So if you want to use ET and ME placeholders rather than drawing out CH2, CH3, that can be really helpful. So what I want you to do is to practice this tonight and see if you're able to get this. I will tell you that a problem like this is very, very likely to show up on your first exam. So it's better to try to get through some of this harder stuff now, but try to work with a partner if you're stuck. Try to utilize each other for help.